So we're going to go ahead and apply the rational equation for our large watershed, acknowledging that this is an oversimplification. I'm going to cover that here in a little bit. So we had the previous information about the watershed area estimates with respect to the various land uses. And we also had given information or received information that said the watershed was 80,640 acres and it had 1.4 inches of rain per hour. Now with that said, we're going to try to do this calculation. So we know that Q equals CIA for the whole watershed, and we've got these different runoff coefficients that I've provided from a standard textbook table. So how are we going to do this? So we're going to have to do Q equals CIA for each land use type, and we're going to have to plug in this 80,640 acres, or half of it, for pasture land. So we're going to go through it and we'll do that adjustment for the percentage of the area at the very end. So for pasture, the C is going to be an estimate. We're going to do something in the middle here, an estimate of 0.35. That's kind of halfway between 0.12 and 0.62. For forest, what are we going to put in for our C in forest? Between 0.05 and 0.25, I kind of just rolled with 0.15. It's like 0.10 away from each of those. Parks and cemeteries, it ranges from 0.1 to 0.25. So what are we going to put there? I just rolled with 0.15 again. Lawns, they represent 20% of the area. A good halfway value for lawns, go with 0.20. It's about 15% away from 0.05, 15% away from 0.35. And impervious. Impervious includes things like roofs, concrete, streets. So we need to be something up near the 0.75 to 0.95 range. So let's just go with 0.85. So once we've got all those calculations done, we can get the numbers, right? And we also have to multiply those numbers by the amount of area that's dedicated to that. So the area that's pasture isn't 80,640 acres. It's half of the area. So it's more like 40,320. How do we count for that? We just multiply by 50%. Forest, we multiply by 10%. So it's Q equals CIA, but the A has to reflect that 10%. Parks and cemeteries, we're going to multiply it at the end by 10%. Lawns by 20%. Impervious by the 10%. Then we'll end up getting some actual values for each of those categories, right? So this one will add up to 19,756.8 CFS. This one adds up to 1,693 CFS. So does this one. It's the same formula actually. Lawns, 4,515.84 CFS. And impervious ends up being 9,596. You can see all these things will sum to a big number, so we sum all those things up. All those numbers here, they all add up to 37,255.68 CFS. Now, I don't necessarily think we need to include the decimal, since, are we really being that accurate? So anyways, it's 37,2055 cubic feet per second, which also could look like this, or the sec could be an S. One thing it's important to note from this exercise is impervious only made up 10% of the watershed area, but of that 37,000, it actually made up probably about a quarter of the actual runoff. And pasture land represented about half of the area, and it represents about half of the runoff. So, just important to take notice of that. So the impervious really had a big impact given it's 10%, because so much of it, only 10% of it actually stays on the ground. So that's just how the rational equation is done. It's easier probably just throwing those numbers into a Microsoft Excel spreadsheet where you've got your C, I, and your A, and then your percent area, and you do a formula that is this equals C times A times area, and then you get that value, and you do that for each of your different land uses with, you know, the coefficient down here for impervious being the 85% runoff one, right? So these are in the same order, and the Excel sheet makes it a lot easier. With all of that said, as we wrap it up, I want to just emphasize there are some limitations here. So I'm going to pull up some information from the Natural Resources Conservation Service, NRCS, which is a government agency that coexists with a lot of the state and state land-grant universities, and been very active in managing soil erosion, especially since the New Deal era, the Roosevelt administration. We'll talk more about the NRCS in a future video. With that said, they say the rational equation was developed about 100 years ago for predicting peak flow rates for small urban watersheds. It's not really good for things that are bigger than 50 acres. So 50 acres is not a whole lot of area. You're talking about like a Walmart parking lot or a Walmart area. So if you're looking at how Walmart may change the land use on a small creek, that probably would work okay. But applying it to a big watershed like Silver Creek, where in our example, we're at tens of thousands of acres, it's a lot bigger than 50 acres. So it's important to kind of know that element of the rational equation. So it also only gives us peak discharges. So it only estimates like what the maximum amount is. So it's not something used for over a wide period of time. So good to know. So we're going to do some review questions really quick. Okay, we'll address these two here in another video, but you should be able to calculate a maximum runoff total from rainfall for a small watershed. You should be familiar with what these terms mean. So Q represents what? It means discharge. And what are some example units for Q? And you should be able to give several. And you should be thinking of volumes per unit time. So example units are not like volume per unit time. You would tell me like examples. So like gallons per minute, cubic feet per second, cubic feet per minute, liters per minute, liters per hour. Any of those are example units for discharge. So a volume per unit time. All right, what are the elements of the rational equation? What goes into it? What's the formula? You should know it's Q equals CIA. Now, let's understand what these coefficients mean. Which of these two coefficients, 0.2 or 0.9, is most likely associated with the asphalt road? And which runoff coefficient here is most associated with the park? So a runoff coefficient, high runoff coefficient, means that most of the water that hits it runs off. So 90% of the water runs off. 20% of the water runs off. So 90% runoff would be your asphalt. And your park, probably something more like 15%, because most of the park, we presume, is green space. So that's all for the actual review questions for this particular one. We're going to do probably one more video on how to diagram stream orders, and the next class we'll start getting into like flooding and flood probability calculations. But for this class, for this Monday, Tuesday kind of class time frame, we're going to do the stream order next.